Welcome to the model answers for the weight and gravity trilogy and triple higher exam questions. Question 1. So we have a 1 Newton weight which is tied to a 30 centimetre long piece of elastic. The other end is fixed to the edge of the table or the bench, and the weight is then pushed off and then bounces up and down on the elastic. So take a second to think of what's actually going to happen. We're going to push off the weight. It's then going to stretch the elastic, moving closer to the floor. Once it's fully stretched, the elastic's going to pull it back up. It's going to propel upwards until it stretches again, at which point it will propel back downwards, and this continues until it comes to a rest. So have a look below. We can see there's a graph which on the y-axis has height from the floor in centimetres, and along the x-axis is time. The graph shows the height of the weight above the floor plotted against time as it bounces up and down and quickly comes to rest. So our first task is to mark on the graph the point F where the weight stops falling freely. So there are a few points on the graph, but I've chosen this first one, which will be the first time that the block stops falling freely. Part B, mark on the graph a point labelled S where the weight finally comes to rest. So when it's come to rest, we shouldn't see there shouldn't be any change in the height that it's moving at now. So it should be where we see a flat line on the graph. So I'll label that point there S. C, mark 2 points on the graph, each labelled M, where the weight is momentarily stationary. So at this point, again, we should see some little flat points, however, only for a moment. So if we look at places on the graph where it changes direction from moving up to moving down, we should find 2 points where it momentarily is stationary. And so these are the 2 points I've chosen whilst it has been stationary. The points represented by the arrows also represent places where you could have put M. On to the next question. For question 2, figure 1 shows a skydiver training in an indoor wind tunnel. Large fans below the skydiver blow air upwards. The skydiver is in a stationary position. Complete the free body diagram for the skydiver. So we've got a force from the air acting upwards, and we've got to draw on an additional force which is acting on the skydiver. Because the skydiver is in a stationary position, the force acting on the skydiver has to be in the opposite direction, and it has to be equal, because the skydiver is not accelerating up or down, so the forces must be balanced. So I'm going to draw the force acting on which is weight, and roughly draw it so that they're equal. So it's 2 marks, one for labelling the force weight, and the other one for drawing the force correctly in the right direction and roughly the same size. Pause the video here because these labels will move in a second. Question 2b, the skydiver now straightens his legs to increase his surface area. This causes the skydiver to accelerate upwards. Explain why straightening his legs causes the skydiver to accelerate upwards. So once the skydiver is accelerating upwards, that tells us that the upward force becomes greater than a downward force. And then this is because the air resistance has now increased due to the increasing of surface area. 2 points for 2 marks. Again, pause the video here because these answers will be removed when we move on to the next question. Part C. skydiver jumps from an aeroplane. There is a resultant vertical force of 300 newtons on the skydiver. There is a horizontal force due to the wind of 60 newtons. And that vertical force, is 300 newtons on the skydiver. Draw a vector diagram on figure 2 to determine the magnitude and direction of the resultant force on the skydiver. Now, the first thing, whenever you're drawing a vector diagram and you want it to be to scale, is to first draw your scale. So I'm going to say that one of these big squares is 60 newtons, and when I did this on paper, I measured that length to be 1.5 centimeters. Okay, now we can actually draw our diagram, making sure it's to scale. So the 300 newtons is going to be 5 large squares, because 60 times 5 equals 300 newtons, vertically upwards. Whilst the horizontal force from the wind is going to be one big square, and I'm going to draw that to the right. Now I'm going to draw a dotted line from the edge of the 60 newtons horizontal force all the way up to in line with the 300 newtons. Now the resultant force is going to be going upwards, but also to the right, because it's got a horizontal component and a vertical component, and I'm going to stop the force in line with that dotted line I've just drawn. Now, after drawing and measuring my resultant force, I found it to be equal to 7 centimeters. I now have to try and work out the magnitude of the resultant force, as it says. We can't see it here, but it just says it just below. Calculate the magnitude of the resultant force. So 1.5 centimeters is equal to 60 newtons. Then we know that 1 centimeter is equal to 40 newtons, and therefore 7 centimeters is going to be equal to 280 newtons. And so therefore the magnitude of the resultant force is equal to 280 newtons. Again, take a second to pause the video, because the answer is about to be taken off the screen. Question 3. The diagram below shows a person using a device called a jetpack. Water is forced downwards from the jetpack and produces an upward force on the person. A. State the condition necessary for a person to be able to remain stationary in midair. So, key word there is stationary, which tells us that the forces acting on that person are balanced. So, if they are balanced, that means there is no resultant force. So, resultant force, those are spelling mistake. So, the resultant force equals 0 newtons, or the upward force is equal to the downward force, which is the weight. Either one of these would get you the mark. Now, part B, the person weighs 700 newtons and the jetpack weighs 140 newtons. Calculate the combined mass of the person and the jetpack. So, we're being asked to calculate, so therefore we're going to be needing to use an equation, and we want to calculate the combined mass of the person and the jetpack. And we also get given some useful information, which I'm going to also underline. So I've underlined. Welcome back. So we have the equation weight is equal to mass times gravity. But in this question we've been asked to calculate the combined mass. So we have to rearrange that equation. So we have mass is equal to weight divided by the gravitational field strength. So we need to work out the combined mass. So we actually need to combine the weights together. So the total weight, or the combined weight, is equal to 840. We get that from plussing 700 to 140. We then divide 840, the weight, divided by 10, the gravitational field strength, which gives us 84 kilograms, which is quite a realistic answer. And so the total answer is 84 kilograms. Now on to part II. Increasing the upward force to 1,850 newtons causes the person to accelerate upwards. Calculate the acceleration of the person and the jetpack and give the unit. So we have to calculate acceleration, which again, because it's a calculate question, means we're going to have to use an equation, and this time we're going to use Newton's second law, which is force is equal to the mass times the acceleration. But again, we're trying to calculate acceleration here, so we need to rearrange that equation to make acceleration the subject. Rearranging that equation, we find that acceleration is equal to the force divided by the mass. So I'm going to underline the new force we've been given of 1,850 newtons, and the mass we're going to use is the combined mass from the previous question. So acceleration is going to be equal to the force, which is 1,850, divided by 84, which gives us an answer of two significant figures, 22, and the units are meters per second squared. And sorry, I've just adapted that a bit. So 22 meters per second squared are the units, and we've used 22 because it's two significant figures. That's the correct answer. Final question, question 4. The diagram shows a child's mobile. The mobile hangs from point P on the ceiling of the child's bedroom. Mark the position of the centre of mass of the mobile by drawing the letter X on the diagram. Do this so that the centre of the X marks the centre of the mass of the mobile. Okay, so whenever you're trying to find the centre of mass, what you need to consider is where the point it suspends is. So we can see it's suspending from point P, and so we need to make sure that where we draw this X is directly below the suspension point. So I've drawn it there, and it's also in the centre of mass in the middle of the aeroplane. So I've drawn it in the middle, or on the same level as the aeroplanes. So exactly what I've just explained, how I chose that location X, just write that as the explanation. It is below this essential point P, and the centre of mass is in the middle of the aeroplanes. 2 points for 2 marks, and we're done.